Tonight, we're going to travel to the edge of everything we have ever known and listen to the last whisper of a machine that should have gone silent decades ago. Right now, as you settle in and the world around you grows quiet, a spacecraft the size of a small car is moving through the darkness between the stars. It has been travelling for nearly 50 years. It carries no crew, it carries no fuel to stop, and it is still talking to us, sending back a thin, ghostly signal that takes more than 22 hours to reach Earth at the speed of the light. That signal is telling us something, and what it is telling us does not match what we expected. 24 billion miles. Let that number breathe for a moment. 24 billion miles from the warmth of the sun, from the blue marble of Earth, from every city and ocean and mountain range you have ever seen or imagined. Voyager 1 is so far away that the sun itself, seen from that distance, is nothing more than an unusually bright star. 1 point among billions, and yet our instruments are still out there, still listening, still measuring the fabric of a place no human eye has ever witnessed directly. The readings it sends back have stunned the scientists who devoted their careers to understanding them. The boundary between our solar system and the galaxy beyond it is not what the model said it would be. The particles are wrong, the plasma is wrong, the magnetic fields are wrong. Something out there, in the dark between the stars, is behaving in ways that current science cannot fully explain. Here is the thing most people never stop to consider. Voyager was not designed to go where it has gone. It was built in the 1970s by engineers who used slide rules and early computers, designed to survive 4 years and photograph the outer planets: Jupiter, Saturn, Uranus, Neptune. That was the mission. And then it kept going, and going, and going, into a region of space that no probe had ever entered, measuring forces and fields and particle densities that exist in a place we had only ever theorized about, from the safety of our own small corner of the universe. The data it is returning now, from the interstellar medium, the true open ocean of the galaxy, is rewriting textbooks. And buried inside those readings are anomalies that remain, to this day, genuinely unresolved, genuinely mysterious, and, if you sit with them long enough, genuinely terrifying. By the end of tonight, you are going to understand exactly why the scientists who study Voyager's transmissions describe their work with a particular kind of reverence and a particular kind of unease. You're going to understand what the heliosphere is, why crossing it changed everything, and what the strange, contradictory signals coming back from beyond it might mean for our understanding of the cosmos. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. There is a signal travelling through the universe right now. It is moving at the speed of light, which means it is covering about 186,000 miles every single second. And yet, despite that almost incomprehensible speed, it still takes more than 22 hours to reach us. 22 hours for a whisper to cross the distance between its source and the antennas we have pointed at the sky. Waiting, listening, recording every faint tremor of data it carries. That signal is coming from Voyager 1, and tonight we're going to follow it back to where it began. Think about what it means for a moment. The speed of light is the fastest thing in the known universe. Nothing we have ever observed moves faster. Light from the sun takes about 8 minutes to reach Earth. Light from the moon takes just over 1 second. These are distances we can almost feel in our bodies, distances with some human texture to them. But the light from Voyager 1 takes more than 22 hours. That single fact, more than any number I could give you, tells you something about where this spacecraft is. It is not merely far away. It is in a category of distance that our minds were never built to process naturally. You have to sit with it. Let it settle. 22 hours at the speed of light. Voyager 1 is, as of right now, the most distant human-made object ever to exist. It launched on September the 5th, 1977, nearly 50 years ago, and it has not stopped moving since. It is currently travelling at roughly 38,000 miles per hour relative to the Sun. That sounds fast, and in human terms it is extraordinarily fast. But space is so vast, so incomprehensibly empty, that even at that speed, Voyager 1 has only covered a tiny fraction of the distance to the nearest star. It is still, in the grandest cosmic sense, practically in our backyard. And yet it is already in territory no human-made object has ever entered before. the first explorer in the truest sense, the loneliest traveller ever set in motion by human hands. When engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, talk about Voyager 1, there is something in their voices that is hard to categorize. It is not quite pride, though pride is certainly there. It is something closer to wonder mixed with a low, quiet disbelief. The spacecraft was designed for a 4-year mission. It was built using technology from the early 1970s, technology that, by today's standards, is almost laughably primitive. Its onboard computer has roughly 100,000 times less processing power than the phone sitting on your nightstand. Its memory capacity is roughly 70 kilobytes. 70 kilobytes. A single low-resolution photograph on a modern smartphone contains more data than Voyager 1 can store in its entire memory bank. And yet here it is, nearly half a century later, still functioning, still transmitting, still doing science. The transmission itself is a kind of miracle. The signal Voyager 1 sends back to Earth is broadcast at 22 watts, roughly the same power as a refrigerator light bulb. By the time that signal crosses more than 24 billion miles of empty space and arrives at the massive dish antennas of NASA's Deep Space Network, it has weakened to a level that is almost beyond imagining. We are talking about a signal so faint that the energy it delivers to our antennas is 20 billion times weaker than the power required to run a single digital watch. And yet we can hear it. We have the technology to pull that whisper out of the noise, to decode it, to translate it into numbers and graphs and data points that scientists can study. That too is a kind of extraordinary thing about what we have built as a species. But here is what makes tonight's story different from any simple celebration of engineering. The data that Voyager 1 is sending back from its current position, deep inside the interstellar medium, the open space between star systems, is not matching our predictions. It is not confirming what the models said it would find. The particle counts are not what they should be. The plasma density is higher than expected, and it has spiked in ways that surprised everyone who was watching. The magnetic field at the boundary of our solar system did not look the way the textbooks described, and there are readings that have been debated for years now, analysed, reanalyzed, and still not fully resolved. Voyager 1 is out there in the dark, sending back dispatches from a place we have never been, and some of what it is reporting does not fit neatly into what we thought we knew. That is the mystery at the heart of tonight's journey. Not a mystery in the science fiction sense. No strange lights. No inexplicable mechanical failure that hints at something watching from the void. The mystery here is quieter and, in its own way, more unsettling. It is the mystery of a universe that turns out to be more complicated than our best models predicted. A boundary that does not behave like a boundary. A region of space that was supposed to be well understood and turns out to contain anomalies that even the scientists closest to the data describe with a particular kind of careful, measured unease. When the people who have spent their careers studying this spacecraft and this region of space use phrases like, "We are not entirely sure," and "this was unexpected, that is worth paying attention to," Voyager 1 crossed the official boundary of our solar system, the heliopause, the point where the sun's influence ends and true interstellar space begins, in August of 2012. It was a moment that made headlines around the world, and rightly so. For the first time in human history, something we had built had left the solar system. It had passed through the invisible membrane that separates our sun's domain from the rest of the galaxy. What lay beyond was not empty exactly, but it was different. It was the interstellar medium, a faint, cold, ancient sea of gas and dust and magnetic fields and particles that drifts between the stars. And Voyager 1's instruments, against all odds, were still alive and measuring it. What those instruments found was not chaos, but it was not the clean, orderly picture the models had drawn either. The magnetic field shifted, but not in the direction scientists had predicted. The density of plasma, charged, ionized gas, was higher than it should have been. Cosmic rays, which are high-energy particles streaming through the galaxy from distant supernovas and other violent events, were flooding in at unexpected angles and in unexpected quantities. Each of these anomalies, taken alone, might be explained away or attributed to measurement error or modelling gaps. But taken together, they form a picture of a boundary and a region of space that is genuinely, productively surprising. And the data is still coming in, so tonight we are going to follow Voyager 1 into the dark. We we are going to trace its journey from the sunlit inner solar system out through the frozen reaches of the outer planets, past the termination shock, through the heliosphere, and across the heliopause into the interstellar medium where it travels now. We're going to look carefully at what it has found there, the expected and the unexpected, the understood and the genuinely mysterious. And we're going to ask what those mysteries might mean, not just for our models of space, but for something larger, for our understanding of where we are and what kind of universe we actually live in. The signal is still coming. Let us listen to what it is saying. To understand why Voyager 1 is out there at all, you have to go back to a specific moment in the 1960s when a young mathematician named Gary Flandreau made a calculation that changed everything. Flandreau was working at NASA's Jet Propulsion Laboratory in 1965, studying the trajectories of potential deep space missions, when he noticed something extraordinary in the orbital positions of the outer planets. Every 175 years, Jupiter, Saturn, Uranus and Neptune align in a configuration that makes something remarkable possible. A spacecraft launched at precisely the right moment, aimed at precisely the right angle, could use the gravity of each planet in turn to slingshot itself to the next one, gaining speed with each pass, travelling the entire outer solar system in a fraction of the time it would take under rocket power alone. The alignment was coming in the late 1970s, and it would not come again until the 22nd century. This was the window, and NASA knew that if they were going to use it, they had to move fast. The mission that eventually became Voyager was conceived under enormous pressure of time. Engineers and scientists had roughly a decade to design, build, test, and launch 2 spacecraft that would need to survive the radiation belts of Jupiter, the freezing temperatures of the outer solar system, and the complete emptiness of interplanetary space, all while running on technology that was, even by the standards of 1977, not cutting edge. The budget was tight, the timeline was punishing, and the margin for error on a mission that would carry humanity's instruments farther than they had ever gone was essentially zero. What they built under those conditions was, without exaggeration, one of the greatest engineering achievements in human history. Voyager 1 and Voyager 2 launched within weeks of each other in the summer and autumn of 1977. Voyager 2 went first, on August the 20th. Voyager 1 followed on September the 5th, launched on a faster trajectory that would allow it to overtake its twin and reach Jupiter first. Both spacecraft were built around a distinctive 10-sided frame, roughly the size and shape of a large umbrella when you include the famous dish antenna. A 3.7-metre wide bowl pointed permanently back toward Earth, like a face turned homeward, even as the body moves away. Attached to long booms extending from the body were the scientific instruments: magnetometers, plasma detectors, cosmic ray sensors, ultraviolet and infrared spectrometers, and a camera platform that would capture the first close images of the outer planets that humans had ever seen. Power was always going to be a problem. At the distances Voyager would travel, solar panels are useless. The sun's light is simply too weak to generate meaningful electricity. Instead, engineers equipped each spacecraft with 3 radioisotope thermoelectric generators, devices that convert the heat released by the natural radioactive decay of plutonium-238 directly into electricity. They are not reactors in the traditional sense. There is no fission, no chain reaction, just the slow, steady, unstoppable warmth of radioactive decay transformed into the electrical current that keeps Voyager alive. When the spacecraft launched, each RTG was producing roughly 470 watts. Nearly 50 years later, due to the gradual decay of the plutonium and the degradation of the thermoelectric converters, that figure has dropped to somewhere around 250 watts. Less power than a few incandescent light bulbs, and yet it is enough, barely, carefully, strategically, to keep the essential systems running. The planetary encounters that followed the launch were nothing short of revelatory. Voyager 1 reached Jupiter in March of 1979 and sent back images that stunned the scientific community and the public alike. The Great Red Spot, the enormous storm that has raged on Jupiter for centuries, resolved into a swirling, complex, almost organic structure. Jupiter's moon Io was revealed to be volcanically active, the most geologically dynamic body in the solar system, with plumes of sulfur erupting hundreds of miles into space. Europa showed a cracked, icy surface that hinted at a liquid ocean beneath. These were not incremental discoveries. They were revelations. Each image that arrived from Voyager was something no human being had ever seen before, beamed back across hundreds of millions of miles by a machine running on the power of a dim light bulb. Saturn came next, in November of 1980. Voyager 1 swept close to the ringed planet and its moons, capturing images of ring structures of breathtaking complexity. Thousands of individual ringlets, gaps, and braided formations that defied simple explanation. It flew close to Titan, Saturn's largest moon and the only moon in the solar system with a thick atmosphere, and discovered that Titan's skies were shrouded in an orange chemical haze, too dense for the cameras to penetrate. This flyby of Titan was a deliberate choice, and it came with a cost. The close approach to Titan bent Voyager 1's trajectory sharply out of the plane of the solar system, sending it above the orbital plane of the planets and onto a course that made any further planetary encounters impossible. Voyager 1's tour of the solar system was over, but its journey was only just beginning. While Voyager 2 continued on to Uranus and Neptune, the only spacecraft ever to visit either planet, Voyager 1 began its long, silent climb out of the solar system. There were no more flybys to plan, no more camera targets, just the slow accumulation of distance year after year, decade after decade, as the spacecraft moved outward through the sparse reaches of the outer solar system at roughly 35,000 miles per hour. The team that had built and operated it shrank over the years. Budgets were cut, instruments were turned off to conserve power, but the mission continued, reclassified and reconceived as the Voyager interstellar mission, with a new and audacious goal: to reach interstellar space itself and to measure it directly for the first time in human history. There is something deeply moving about that persistence. The people who launched Voyager 1 in 1977 could not have known with certainty that it would still be functioning nearly 50 years later. They hoped. They engineered conservatively, built in redundancies, designed systems to last as long as possible. But no one could guarantee that a spacecraft travelling through the unknown would survive. And yet it did. It does. Right now, as you listen to these words in the quiet of the night, Voyager 1 is out there, moving through the cold dark between the stars, its plutonium still decaying, its antenna still locked onto Earth, its remaining instruments still taking measurements of a place that no probe had ever reached before. It is the farthest thing we have ever sent anywhere, and it is still speaking. The question that drives everything that follows is a simple one. What is it saying? On February the 14th, 1990, a command was sent from Earth to a spacecraft that was then about 3.7 billion miles away. The command was simple in technical terms, but extraordinary in its intention. It asked Voyager 1 to do something it had not done in years, to turn its camera platform around and point its instruments back toward the inner solar system, back toward home. The camera was old by then, its systems strained from years of cold and radiation. There was genuine concern among engineers that rotating the platform might damage it permanently. But the scientist who had championed the idea for years, Carl Sagan, had argued that the image was worth the risk, that what it would show humanity was something we needed to see. And so the command was sent, and Voyager 1 turned and looked back and took the photograph that would become one of the most important images ever made. What the camera captured was almost nothing. Against the scattered light of the sun, caught in one of the camera's exposure bands like a mote of dust in a sunbeam, was a pale, bluish-white point of light less than 1 pixel across. Barely there. Almost invisible. That point of light was Earth, every human being who had ever lived. Every city, every ocean, every mountain range, every war and every act of love and every moment of suffering and every burst of laughter in the entire history of our species, compressed into a single dot so small that it nearly vanishes into the background. Carl Sagan wrote about that image with a kind of aching clarity that has never been surpassed. He called it the pale blue dot, and in doing so, he gave us one of the most humbling pieces of perspective any scientific instrument has ever produced. But here is what I want you to hold in your mind tonight, as you lie there in the dark. When Voyager 1 took that photograph, it had already been travelling for 13 years. 13 years at tens of thousands of miles per hour, moving constantly outward, and it was still close enough to Earth that our planet was visible, if only barely, in its cameras. That is how vast the solar system is. That is the scale of the space that Voyager 1 still had ahead of it. The distance it had already covered, which seemed almost infinite from a human perspective, was in cosmic terms barely a beginning. Beyond the pale blue dot, beyond the orbits of the outer planets, beyond even the distant region where Pluto drifts in the cold, there stretched billions more miles of space before Voyager would reach anything resembling a boundary. The photograph was not an ending. It was a threshold. To understand what lay beyond that threshold, it helps to think about what the solar system actually is. Most people carry a mental image of the solar system that looks something like a diagram from a school textbook. The sun in the center, the planets arranged in neat concentric rings, everything relatively close together, everything bathed in warmth and light. That image is, in almost every meaningful way, wrong. The solar system is not a tidy set of rings. It is an enormous, irregular bubble of space dominated almost entirely by the sun's gravity and the sun's wind, a constant outflow of charged particles that streams outward from the solar surface in all directions at about 1 million miles per hour. That wind does not stop at Neptune. It does not stop at Pluto. It keeps going, pushing outward into space, thinning and slowing as it travels, until it finally loses the battle against the pressure of interstellar space pressing in from outside. The outer boundary of that bubble, the place where the sun's wind finally gives way, is called the heliopause, and it is far, far beyond anything most people imagine when they picture the edge of the solar system. When Voyager 1 took the pale blue dot photograph in 1990, it was still inside this bubble, still travelling through the heliosphere, the region of space shaped and dominated by the sun. Between it and the heliopause lay billions more miles of thinning solar wind, a region called the Helios Heath, and before that a dramatic boundary called the termination shock, where the solar wind abruptly slows from supersonic to subsonic speeds. Voyager 1 would not reach the termination shock for another 14 years. The heliopause itself would take 22 years from the moment that photograph was taken. The scale involved is so large that even Voyager 1, the fastest and most distant human-made object ever built, needed decades of continuous travel to cross it. And yet, somehow, that photograph changed the way we understood the journey. Before the pale blue dot, Voyager 1 was a scientific instrument on a trajectory. After it, it became something else, a messenger, a witness, a kind of ambassador from a civilization small enough to fit into a single pixel. The image did something that all the numbers and distances and scientific papers in the world had struggled to do. It made the scale of space feel real. It made the smallness of Earth feel real. And in doing so, it made the question of what lay beyond, what Voyager would find as it moved further and further from that tiny dot, feel urgent in a way that was not purely scientific. It felt personal. It felt like something that mattered to what we are and where we come from. In the years that followed the photograph, Voyager 1 continued its climb. The cameras were turned off to save power. There was nothing left close enough to photograph, and the energy required to run the imaging systems was needed elsewhere. But the other instruments kept running. The magnetometer, measuring the direction and strength of the magnetic field threading through space. The plasma wave instrument, listening for the vibrations of charged particles in the solar wind. The cosmic ray detectors, counting the high-energy particles streaming in from the galaxy beyond. Each of these instruments was gathering data from a region of space that grew stranger and more unfamiliar with every passing year. And slowly, gradually, the readings began to change in ways that told scientists something profound was approaching. The solar wind was slowing. The magnetic field was shifting. The cosmic ray counts were rising. Voyager 1 was approaching the edge. That edge, the true outer limit of our sun's dominion over space, is not a wall or a line you could see or touch. It is more like a shoreline, where the waves of one ocean meet the currents of another, where the sun's breath finally gives out and the ancient cold wind of the galaxy takes over. Voyager 1 was heading for that shoreline with no ability to stop, no ability to turn back, carrying instruments that its creators had dared to hope would still be alive when it arrived. And as you rest here tonight, I want you to carry with you the image of that pale blue dot, that barely visible pixel of light, and the incomprehensible darkness that surrounds it. Because everything that follows in tonight's journey takes place out there, in that darkness, far beyond the dot, far beyond anything we ever thought we would reach. There is a bubble wrapped around our entire solar system. You cannot see it. You cannot feel it. No human being has ever looked up at the night sky and watched its edges glow or shimmer, and yet it is real, measurable, mappable, and in ways that scientists are only beginning to fully appreciate, absolutely essential to the existence of life on Earth. It is called the heliosphere, and it is the Sun's great invisible gift to everything that orbits it. Tonight, before we can understand what Voyager 1 found when it left this bubble behind, we need to understand what the bubble actually is. Because the heliosphere is not simply empty space with a fancy name, it is a dynamic, constantly moving, enormously complex structure, and the fact that it exists at all is one of the more quietly astonishing things about our corner of the galaxy. The heliosphere begins with the Sun itself. Every second, the Sun is releasing a stream of charged particles, mostly electrons and protons, that pour outward from its surface in all directions at roughly 1 million miles per hour. This is the solar wind. It is not a metaphor or a poetic description. It is a real, physical flow of matter, thin by earthly standards but continuous and relentless, sweeping outward through the solar system like the breath of an enormous living thing that never stops exhaling. The solar wind is what makes comet tails always point away from the Sun, regardless of which direction the comet is travelling. It is what causes the auroras at Earth's poles, when the wind interacts with our planet's magnetic field and channels particles down into the upper atmosphere, where they collide with gas molecules and produce those pale, shimmering curtains of green and violet light. The solar wind is everywhere inside the heliosphere, all the time, filling the space between the planets with a thin but measurable flow of solar material. As the solar wind moves outward, it does not simply continue forever at the same speed. Space is not empty in the absolute sense. Even in the vast reaches beyond Neptune, there is material. A diffuse mix of gas, dust, and particles known as the interstellar medium, the substance that fills the space between star systems throughout the galaxy. The interstellar medium has its own pressure, its own magnetic field, its own slow drift, and at some point far out in the solar system, the outward pressure of the solar wind meets the inward pressure of the interstellar medium, and something remarkable happens. The solar wind cannot simply punch through, it has to slow down. And when a supersonic flow of gas suddenly slows, it does not do so gently. It hits what physicists call a shock wave, a sharp boundary where the character of the flow changes abruptly. This boundary is called the termination shock, and it is the first of several nested layers that make up the outer structure of the heliosphere. Voyager 1 crossed the termination shock in December of 2004, at a distance of about 94 astronomical units from the Sun, roughly 94 times the distance between Earth and the Sun, or about 8.7 billion miles. The crossing was not a gentle transition. The instruments on board recorded a dramatic change in the behaviour of the solar wind. It slowed from supersonic to subsonic speeds almost instantaneously in the context of space travel. The magnetic field strengthened. The density of the plasma around the spacecraft increased. It was, in the language of the scientists studying the data, unmistakable. Voyager 1 had entered a new region, a thick, turbulent shell of slowed solar wind that lies between the termination shock and the true outer edge of the heliosphere. This region is called the Helios Heath, and it turned out to be stranger and more complex than anyone had expected. Here is the thing most people do not realize about the heliosphere. It is not a perfect sphere. The Sun is not sitting still in space. It is moving through the galaxy at roughly 43,000 miles per hour, carrying the entire solar system with it. As it moves, the solar wind pushes out ahead of it like the bow wave in front of a ship, while the heliosphere stretches out behind into a long tail, like a comet. The result is a shape that scientists describe as roughly like a deflated beach ball, or perhaps more accurately like a vast, lopsided bubble with a blunt leading edge and an elongated trailing wake that may extend for hundreds of billions of miles in the direction the Sun has come from. Voyager 1 is exiting through the leading edge, the blunt nose of the heliosphere that faces the direction of the Sun's motion through the galaxy. This matters enormously for what it is finding, and for why what it is finding is so surprising. The heliosphere also serves a function that is easy to overlook but impossible to overstate. It is a shield. The galaxy is full of cosmic rays, high-energy particles accelerated to enormous speeds by the violent events of the cosmos, supernova explosions, the jets of black holes, the collisions of neutron stars. These particles travel through the galaxy at a significant fraction of the speed of light, carrying energies that would be lethal to living cells in sufficient doses. The heliosphere deflects and absorbs a substantial fraction of these cosmic rays before they can reach the inner solar system. Earth's own magnetic field provides an additional layer of protection, but without the heliosphere as the first line of defense, the cosmic ray environment at Earth's surface would be significantly more intense than it is today. We live, in a very real sense, inside a shield that the sun has built around us, and Voyager 1 is now on the other side of that shield, in a place where the cosmic rays flow freely from every direction. When you think about the heliosphere this way, not as a boundary to be crossed, but as a structure that has made complex life possible on at least one planet, the data Voyager is sending back from beyond it takes on a different weight. This is not just a story about a spacecraft traveling into unknown territory. It is a story about the limits of the environment that made us. Every reading Voyager 1 takes in the interstellar medium is a measurement of the universe as it exists outside our cocoon, unfiltered, unshielded, ancient and cold and indifferent in a way that the space inside the heliosphere, warmed and shaped by the sun's constant breath, simply is not. The heliosphere is home. What lies beyond it is something else entirely, and what Voyager is finding out there, in that something else, is where tonight's deeper mystery truly begins. The year was 2012. Voyager 1 had been travelling for 35 years. It had covered more than 11 billion miles, and the scientists watching its instruments from the Jet Propulsion Laboratory in Pasadena were seeing something in the data that made them sit forward in their chairs. The readings had been changing for months, gradually, then more rapidly, then in ways that were unmistakable even to the most cautious interpreters. The solar wind particles that Voyager had been swimming through for 3.5 decades were disappearing. The cosmic ray counts were surging. Something was happening at the boundary, something definitive, something that had never happened to any human-made object before. Voyager 1 was approaching the heliopause, the true outer edge of the sun's domain, and the instruments could feel it coming. The crossing itself was not a single moment you could point to on a clock. Space does not work that way. Boundaries in the cosmos are rarely sharp lines. They are more often gradual transitions, zones of mixing and turbulence where one regime gives way to another over thousands or millions of miles. But within the context of Voyager 1's journey, the transition was remarkably abrupt. In the late summer of 2012, over a period of just a few days, the plasma instrument recorded an almost complete dropout of solar wind particles, the charged material that the sun had been pumping outward continuously for billions of years and that Voyager had been immersed in for its entire journey. At the same time, the cosmic ray instrument recorded a sharp and sustained increase in galactic cosmic rays, particles streaming in from the interstellar medium from sources scattered across the galaxy. The two curves crossed on the instrument readouts like lines on a graph marking a threshold. Solar material falling, galactic material rising. Voyager 1 had crossed over, but here is where the story becomes genuinely complicated. And this complication is important because it reveals something about how science actually works, and about how the universe resists our attempts to categorize it cleanly. The magnetic field did not change. That was the problem. Every model of the heliopause that scientists had constructed predicted that when a spacecraft crossed from the heliosphere into interstellar space, it would detect a clear shift in the direction of the magnetic field. Inside the heliosphere, the magnetic field is dominated by the sun. It spirals outward in a structure called the Parker spiral, shaped by the sun's rotation. Outside the heliopause, in the interstellar medium, the galactic magnetic field should dominate, running in a different direction entirely. When Voyager 1's magnetometer readings came in from that August crossing, the direction of the magnetic field had not changed. Not significantly, not in the way the models predicted, and that single fact threw the entire interpretation of the crossing into doubt. For months, the scientific community debated what the data meant. Papers were written, conference presentations were made. Some scientists argued that Voyager had not actually crossed the heliopause, that it had entered some previously unknown region, perhaps a kind of magnetic highway within the heliosheath, where cosmic rays could move freely, but where the magnetic field still carried a solar signature. Others argued that the heliopause itself was simply more complex than the models assumed, that the magnetic field transition might be gradual rather than sharp, and that Voyager was in the process of crossing it even if the crossing did not look the way everyone had expected. The debate was not a failure of science, it was science working exactly as it should. A community of careful, rigorous people wrestling honestly with data that did not fit neatly into existing frameworks. The resolution came slowly and it came through continued observation. By the time Voyager 1 had travelled another year deeper into the region beyond the heliopause, the accumulated data made a compelling case. The plasma density had increased dramatically, consistent with the denser environment of the interstellar medium compared to the heliosphere. The cosmic ray flux had stabilised at a new, higher level consistent with the galactic background. The pattern of particle flows had changed in ways that matched the predictions for interstellar space, even if the magnetic field transition remained puzzlingly smooth. In 2013, NASA announced officially that Voyager 1 had indeed entered interstellar space, that it was beyond any reasonable scientific doubt the first human-made object to have left the heliosphere and entered the space between the stars. It was a moment that deserved every headline it received. And yet the magnetic field anomaly did not go away. It remained in the data, a quiet puzzle sitting at the edge of the celebration. Scientists proposed explanations. Perhaps the interstellar magnetic field in Voyager's local neighbourhood happened to be nearly aligned with the solar magnetic field by coincidence, an accident of geometry. Perhaps the heliopause in this particular region was unusually smooth and did not produce the kind of turbulent mixing that would generate a sharp directional shift. Perhaps the models of the heliospheric magnetic structure needed revision in ways that the community had not yet fully worked out. Each of these explanations was plausible. None was fully satisfying. And that residual uncertainty, that honest, careful acknowledgement that the data contained something not yet fully understood, is part of what makes Voyager 1's story so compelling and so alive. What strikes me most about the crossing, when I sit with it, is not the triumph of the engineering or even the beauty of the scientific discovery. It is the scale of what that boundary represents. The heliopause is not just a line on a map. It is the edge of the sun's influence, the outermost reach of the force that created Earth, that warms every ocean and drives every weather system, and makes photosynthesis possible and sustains every living thing that has ever existed on this planet. To cross that boundary is to leave behind, in a very real physical sense, the domain of our star. On the other side is space that the sun does not touch in any meaningful way. Space that belongs, if it belongs to anything, to the galaxy itself. Cold, ancient, swept by forces originating from sources billions of miles away in every direction. Voyager 1 crossed into that space in the summer of 2012. And what it found there, in the years that followed, is what tonight's deeper mystery is made of. Imagine standing outside on a calm night, sheltered from the wind by the walls of a house. You can hear the wind out there, you know it exists, but you are protected from it. Now imagine stepping out from behind that shelter. Suddenly the wind hits you from all directions, not just from one side, but from everywhere at once, as if the air itself has been set into motion by forces operating on a scale far larger than anything nearby. That is something like what Voyager 1's cosmic ray detectors experienced as the spacecraft crossed the heliopause and entered interstellar space. The cosmic rays, high-energy particles that stream through the galaxy from violent events scattered across billions of light-years, were suddenly arriving from all directions, at intensities that the models had predicted but whose details, on closer examination, turned out to be wrong in ways that scientists are still working to fully understand. First, let us be clear about what cosmic rays actually are, because the name is slightly misleading. They are not rays in the way that light is a ray. They are particles, mostly protons but also helium nuclei and heavier atomic nuclei, that have been accelerated to enormous speeds by the most energetic events in the universe. Supernova explosions, which occur when massive stars collapse and detonate at the end of their lives, are one of the primary sources. The jets produced by black holes at the centres of galaxies are another. When these cataclysmic events occur, they fling particles outward at velocities approaching the speed of light, and those particles then travel through the galaxy, bouncing off magnetic fields and gradually diffusing in all directions. By the time they reach our corner of the Milky Way, They have been travelling for potentially millions of years, carrying energy signatures that encode the violence of their origin points in ways that physicists can read and study. Inside the heliosphere, the sun's magnetic field and the outward pressure of the solar wind act as a partial barrier to these incoming galactic cosmic rays. They do not block them completely. Cosmic rays are energetic enough to penetrate even significant magnetic shielding, and some fraction of them reach Earth regardless. But the heliosphere reduces the cosmic ray flux meaningfully, particularly at lower energy levels. When Voyager 1 was travelling through the inner and middle solar system, its cosmic ray detectors were measuring a population of particles that had been filtered and partially deflected by the heliosphere's protective influence. Outside the heliopause, that filter is gone, and what Voyager found when the filter was removed was both expected and deeply puzzling at the same time. The expected part was the increase in cosmic ray intensity. Scientists had predicted that once Voyager crossed into interstellar space, it would detect a higher flux of galactic cosmic rays, more particles arriving per second, coming from a wider range of directions. That prediction was confirmed. Cosmic ray counts went up sharply at the crossing, and then stabilized at a new, higher baseline. But the details of that increase, the specific energies of the particles, the precise directions they were arriving from, the way the flux varied over time, did not match the standard models with the precision that scientists had hoped for. The discrepancies were not enormous. They were not the kind of thing that makes you throw out the underlying physics entirely. But they were real, reproducible and persistent. And in science, a persistent discrepancy between prediction and observation is always worth taking seriously. One of the most interesting anomalies involves the so-called anomalous cosmic rays, a specific population of particles that behave differently from the standard galactic cosmic ray background. These are particles that originate from neutral atoms drifting in from the interstellar medium, which get caught up in the solar wind, ionized by the sun's radiation, and then accelerated at the termination shock to high energies. They are, in a sense, cosmic rays manufactured by the boundary between the heliosphere and interstellar space itself. Models predicted that once Voyager 1 crossed the heliopause, these anomalous cosmic rays would effectively disappear, because the acceleration process that creates them happens inside the heliosphere, and Voyager would be beyond the region where they concentrate. Instead, Voyager 1 continued to detect them outside the heliopause, at levels and distributions that did not fit the simple picture. Something about the boundary region was sustaining or trapping these particles in ways the models did not account for. Here is the thing most people do not realize about cosmic ray research. These particles are not just a scientific curiosity, they are one of our primary tools for understanding the structure and history of the galaxy itself. The composition of cosmic rays, the ratio of different elements and isotopes, encodes information about which stars exploded, how long ago, and in what kinds of environments. The energy spectrum of cosmic rays tells us about the magnetic field structure of the interstellar medium and the nature of the acceleration mechanisms that produced them. When our models of how cosmic rays behave at the boundary of the heliosphere turn out to be imprecise, it is not just a local problem. It means our understanding of how particles propagate through the galaxy, a foundational question in astrophysics, needs to be revised. Voyager 1's anomalous readings are not a footnote. They are a challenge to some of our most basic assumptions about the physics of interstellar space. There is also something quietly terrifying about the raw fact of what cosmic rays represent. Each particle that Voyager 1's detectors register as it moves through the interstellar medium is a piece of shrapnel from some ancient catastrophe, a star that died perhaps millions of years ago, somewhere across the galaxy, its death so violent that the energy of the explosion is still travelling through space, still moving, still carrying the signature of that moment of destruction. The interstellar medium is full of this shrapnel. It drifts through the dark between the stars in all directions at all times, a constant invisible rain of energetic particles that has been falling through the galaxy since long before our sun was born. Inside the heliosphere, we are partially shielded from it. Outside, Voyager 1 moves through it freely, measuring it directly for the first time, finding that it does not behave quite as cleanly as we hoped. And there is one more layer to this puzzle that deserves to be named plainly. The fact that the cosmic ray readings outside the heliopause do not perfectly match the predictions is not, by itself, an extraordinary crisis for physics. Models are always approximations. Predictions are always based on incomplete information. What makes this particular set of discrepancies worth sitting with, worth exploring slowly and carefully on a night like tonight, is that they are not isolated. The cosmic ray anomalies are one piece of a larger pattern. The plasma density is also wrong. The magnetic field transition was also unexpected. Multiple independent instruments on the same spacecraft are painting a picture of the interstellar medium that, in its details, keeps surprising the people who know it best. When every instrument on the only probe we have ever sent into interstellar space comes back with data that challenges the models in different ways, the combined weight of those surprises is something you cannot easily dismiss. It is something that demands a deeper look, and that deeper look is exactly where we're going next. There is a substance filling the space between the stars. It is not nothing, though it is closer to nothing than anything you have ever encountered in your daily life. It is plasma, a diffuse, ionized gas made up of electrons and protons that have been stripped apart from each other by the energy of the cosmos, drifting through the interstellar medium in quantities so thin that a cubic meter of it would contain fewer particles than the best vacuum we can create in a laboratory on Earth. This substance is ancient. It has been drifting through the galaxy for billions of years, shaped by the magnetic fields threading through interstellar space, stirred occasionally by the shock waves of distant supernovas, carrying within its faint density and temperature a record of the galaxy's long and violent history. And when Voyager 1's plasma wave instrument began taking direct measurements of it from inside the interstellar medium, what it found was not what the models had said it would be. The plasma wave instrument on Voyager 1 does not measure plasma density directly in the way you might measure the temperature of a room with a thermometer. Instead, it listens. It detects oscillations, vibrations in the plasma that propagate at specific frequencies determined by the density of the medium they are moving through. This is called a plasma oscillation event, and the physics behind it is well established. When something disturbs a region of plasma, a burst of energy from a solar event, a shock wave rippling outward from the sun, it sets the local plasma vibrating at a frequency that is mathematically related to the number of particles per cubic meter in that region. By measuring the frequency of the oscillation, scientists can calculate the density of the plasma Voyager 1 is swimming through. It is an elegant, indirect method, and the numbers it has produced since 2012 have been consistently, persistently higher than expected. The first clear plasma density measurement from interstellar space came in October of 2013, about a year after the heliopause crossing. A burst of solar activity sent a pressure wave outward through the heliosphere, a coronal mass ejection, a cloud of magnetized plasma erupting from the sun's surface, and that wave eventually reached Voyager 1 more than a year later, having travelled billions of miles through the heliosheath and across the heliopause into the interstellar medium. When the wave hit the local plasma, it set it oscillating, and the plasma wave instrument caught the signal. The frequency of that oscillation implied a plasma density roughly 40 times higher than the density inside the heliosphere near the heliopause. That was broadly consistent with what models of the interstellar medium had predicted. The interstellar medium is denser than the outer heliosphere, but the specific number was at the high end of what the models expected. Noted, filed, studied. Then it happened again. In 2014, another solar-driven pressure wave reached Voyager 1 and triggered another plasma oscillation event. The density measurement came back higher still, even higher than the first reading. The spacecraft had moved farther into interstellar space, and instead of finding plasma density leveling off or decreasing as the local environment became more uniform, it found the density climbing. A third event, detected in 2017, confirmed the trend. As Voyager 1 moved deeper into the interstellar medium, the plasma it was measuring was getting progressively denser. 3 independent measurements, across 4 years of travel covering hundreds of millions of additional miles, all pointing in the same direction. This was not noise. This was not a calibration error. This was a real, reproducible signal from the universe, and it did not match the picture that the standard models of local interstellar space had painted. Here is the thing most people do not realize about models of the interstellar medium. We built those models without ever having a probe inside the interstellar medium to test them against. Everything we knew about the local interstellar environment before Voyager 1 crossed the heliopause came from remote observations, measuring how light from distant stars was absorbed or scattered by the gas between them and us, detecting the radio emissions of hydrogen atoms in the interstellar medium, inferring density and temperature from the behavior of cosmic rays. These are powerful techniques, and they gave us a reasonable first-order picture of what the local interstellar medium should look like. But they are indirect. They are integrations over large volumes of space. They cannot tell you what the plasma density is in one specific cubic meter at one specific location. Only a probe inside the medium can do that, and the probe is telling us something the remote observations did not prepare us for. Scientists have proposed several explanations for the rising plasma density readings. One possibility is that Voyager 1 is travelling through a region of the local interstellar medium that is not perfectly uniform, that there is genuine small-scale structure in the plasma density, pockets of higher and lower density that the spacecraft is passing through as it moves. Another possibility involves the nature of the heliopause itself. The boundary between the heliosphere and the interstellar medium may not be a clean, static surface. It may be dynamic, oscillating, pushing and pulling as the solar wind pressure varies with the Sun's activity cycle. If the heliopause is oscillating, it may be sweeping plasma from the heliosheath outward into the near interstellar medium, locally enriching the density just beyond the boundary in ways that create a gradient Voyager 1 is still moving through. These are plausible ideas. They are being actively studied. None of them has yet produced a model that fully accounts for all three density measurements in a way the entire community finds compelling. What makes the plasma density mystery particularly resonant tonight is what it implies about the nature of the boundary we crossed. We tend to think of the heliopause as a wall, a clear definitive line where one thing ends and another begins. The Sun's domain on one side, the galaxy's domain on the other, clean, categorical. But the plasma density reading suggests something more ambiguous. The boundary region is not clean. It is messy, transitional, possibly dynamic, in ways that blend the two environments together for some distance on either side. The interstellar medium just beyond the heliopause is not a pristine, undisturbed sample of the galaxy at large. It has been shaped, compressed, and perhaps enriched by the very presence of the heliosphere pushing against it from the inside for billions of years. The Sun has left its mark on the space just beyond its own reach, in ways we're only now beginning to measure. And this is what I want you to carry with you as you rest tonight. The image of that instrument, riding aboard a 50-year-old machine in the cold dark between the stars, listening to the faint vibrations of plasma so thin it barely exists, and finding in those vibrations a number that does not match what we wrote in the textbooks. It is a small discrepancy in absolute terms, a factor of a few, in a region where everything is already almost nothing. But science is built on exactly these kinds of small, persistent discrepancies, the readings that do not quite fit, the measurements that force you to go back to the model and ask what you missed. Voyager 1 is out there asking that question on our behalf, in a place no other instrument can reach. And the universe so far has not given us a complete answer. In the spring of 2022, something went wrong. Engineers at NASA's Jet Propulsion Laboratory were performing their daily routine of receiving and analysing the data stream coming from Voyager 1, a ritual that had been carried out in one form or another for nearly 45 years. But on this particular day, the data they received did not make sense. The spacecraft's attitude articulation and control system, one of the onboard computers responsible for keeping Voyager oriented correctly in space and for packaging the scientific data for transmission, was sending back information that was garbled, nonsensical, a stream of numbers that did not correspond to any valid readout of the spacecraft's actual status or the readings from its instruments. The science data was still being collected. The housekeeping telemetry, the basic vital signs of the spacecraft, was still intact. But the system responsible for communicating that information to Earth had begun producing gibberish, and no one immediately knew why. To appreciate the particular anxiety of that moment, you have to understand the communication environment that the Voyager team works in. When Voyager 1's engineers identify a problem and want to send a corrective command, they cannot simply type something and see the result a few seconds later. The signal takes more than 22 hours to reach the spacecraft at the speed of light. Then they must wait another 22 hours for Voyager's response to travel back. Every single diagnostic attempt, every command sent to probe the nature of the fault, every proposed fix, each one costs nearly 2 days of waiting. A troubleshooting session that might take an hour on a computer sitting in front of you takes weeks or months when your computer is 24 billion miles away. This is the reality of deep space engineering, and it requires a particular kind of patience and precision that most people will never need to exercise in any other domain of human activity. The team began methodically working through the possibilities. The first task was simply to understand what was producing the garbled output. Voyager 1 has 3 onboard computers, a heritage of redundancy that the engineers of the 1970s built in, specifically because they knew that over the course of a decades-long mission, hardware failures were inevitable. The flight data system computer, the one responsible for collecting data from the science instruments and packaging it for the radio transmitter, appeared to be the source of the problem. But diagnosing a computer fault on a spacecraft moving through interstellar space is not like opening a machine and looking at its components. It is a process of inference, of sending carefully designed test commands and reading the responses, of reconstructing the internal state of a system from the outside, one agonizing transmission cycle at a time. Weeks passed, then months. The team sent commands, they waited. They analyzed the responses, they sent more commands. Through this slow, painstaking process, they gradually built up a picture of what had happened. A single chip in the flight data system computer, one specific memory location responsible for storing a portion of the software that packages the science and engineering data, had become corrupted. It was not producing random errors at random times. It was consistently misreading or miswriting a specific block of information, causing the output stream to be mangled in a systematic way. The corruption was not spreading. The chip was not failing entirely. It was a localized fault in a very old piece of hardware that had been operating in the radiation environment of interstellar space for nearly half a century. In some sense, the remarkable thing was not that it had happened. The remarkable thing was that it had taken this long. The fix that the team devised was an elegant piece of remote engineering. Rather than trying to repair the corrupted memory location, which was not possible from Earth, they restructured the software around it. They identified all the code that had been stored in or was passing through the damaged chip location, and they redistributed it across other available memory locations on the computer, essentially routing the spacecraft's software around the broken section, the way traffic is rerouted around a closed road. This solution required rewriting and redistributing code across a computer architecture that was designed in the early 1970s, documented in engineering files that were decades old, maintained by a team that included engineers who had joined the mission in its early years alongside much younger colleagues who had learned the system's arcane details specifically to keep it alive. It was, without exaggeration, one of the most impressive feats of remote diagnostic engineering ever performed. The fix was implemented in stages throughout 2023. Each stage required sending a carefully constructed command, waiting nearly 2 days, and verifying that the response matched what was expected before proceeding to the next step. By the end of the process, all 4 of Voyager 1's active science instruments were once again returning coherent, usable data. The plasma wave instrument, the magnetometer, the cosmic ray detector, the low-energy charged particle instrument. All 4 were operational, all 4 were transmitting real readings from interstellar space, and all 4 had data gaps from the months of the communication crisis that scientists immediately set about analysing for whatever information could be salvaged. The spacecraft was alive, the mission continued, and the data that came back after the fix revealed something that gave the team a new puzzle to consider. During the period of the computer fault, some of the instrument readings that were recovered from the scrambled data stream, after painstaking reconstruction, showed fluctuations in the plasma environment around Voyager, one that had not been seen before in quite the same way. The plasma wave instrument in particular had captured oscillation events during the disrupted period, whose characteristics added new data points to the ongoing puzzle of interstellar plasma density. The very crisis that had threatened to silence the spacecraft had also, inadvertently, produced a period of observation that filled in gaps in the long-term record of Voyager 1's environment. Science, sometimes, finds a way to extract signal even from noise. What the whole episode revealed beyond its immediate scientific content was something about the nature of this mission that is easy to forget when you think of Voyager 1 as simply a distant sensor floating passively through space. It is not passive. It is actively maintained, actively monitored, actively fought for by a community of engineers and scientists who have dedicated careers, in some cases entire lifetimes, to keeping this machine alive and speaking. Every piece of data that Voyager 1 returns from the interstellar medium exists because human beings on Earth are paying attention, solving problems, refusing to give up on a spacecraft that by any reasonable measure should have gone silent decades ago. The signal that comes back across 22 hours of light-speed travel carries within it not just the readings of the interstellar medium, but the accumulated ingenuity and devotion of everyone who has kept the transmission alive. That, too, is worth sitting with in the quiet of tonight. There is an invisible architecture threading through the universe. It has no mass. You cannot hold it or see it or feel it directly, and yet it shapes the motion of every charged particle in the cosmos, from the electrons spiraling around field lines in the atmosphere of a distant pulsar to the solar wind particles deflected around Earth's magnetosphere on a quiet Tuesday afternoon. Magnetic fields are everywhere in space, generated by moving charged particles, sustained by the dynamics of plasma, stretched and twisted and compressed by the large-scale motions of cosmic gas. They are one of the fundamental organizing forces of the universe, and the place where the sun's magnetic field ends and the galaxy's magnetic field begins, the precise seam between those two vast and ancient structures, is exactly where Voyager 1 is traveling right now. What it has found at that seam does not look the way we thought it would. To understand why the magnetic field at the heliopause matters so much, you need to hold two pictures in your mind at the same time. The first is the sun's magnetic field. The sun is a rotating sphere of plasma, and as it rotates, it generates a powerful magnetic field that extends outward through the solar system. As the solar wind carries this field outward from the sun, the rotation of the sun winds it into a spiral, like water from a spinning garden sprinkler. This structure, called the Parker spiral after the physicist Eugen Parker, who first described it mathematically in 1958, fills the entire heliosphere. The direction of the magnetic field lines in this spiral is roughly in the plane of the solar system, winding around the sun in great arcs that become more and more stretched and elongated as you move toward the outer edges of the heliosphere. By the time you reach the heliopause, the field lines are nearly perpendicular to the direction of travel outward from the sun. The second picture is the galactic magnetic field. The Milky Way, like all spiral galaxies, is threaded with a large-scale magnetic field that runs roughly parallel to the plane of the galactic disk, tracing the spiral arms of the galaxy in a vast, slowly varying structure that has been built up over billions of years by the motions of interstellar gas, the explosions of dying stars, and the rotation of the galaxy itself. This galactic field has a direction. It points in a specific orientation in three-dimensional space, an orientation that is measurably different from the direction of the sun's field in the outer heliosphere. Models of the heliopause had predicted that as Voyager 1 crossed from the heliospheric field into the galactic field, the magnetometer would record a clear change in the direction the field lines were pointing, a rotation, a shift, the signature of one magnetic domain giving way to another. That signature, as we have already touched on, was frustratingly absent from the data, but the magnetic field story does not end with that absence. In the years since the crossing, Voyager 1's magnetometer has continued to record the galactic magnetic field in the interstellar medium, building up a picture of its behavior across a widening range of distances from the heliopause. And that picture is turbulent, not chaotic. The galactic field has a clear large-scale direction that the data confirms. But on the scales that Voyager 1 is sampling, the field is not smooth and uniform the way a simple model would suggest. It fluctuates. It varies in strength. It shows oscillations and perturbations that indicate the local interstellar medium is far from the quiet, undisturbed environment that early models assumed. The space between the stars, it turns out, is not calm. It is subtly, persistently restless, stirred by forces operating on timescales and length scales that dwarf anything in our immediate solar neighborhood. One particularly striking feature of the magnetic field data from Voyager 1 is a persistent enhancement in field strength that was detected in the region just inside the heliopause, a zone that scientists have come to call the magnetic barrier. As the solar wind slows and piles up in the heliosheath before crossing the heliopause, the magnetic field carried by that wind also piles up and intensifies, creating a region of elevated field strength right at the inner edge of the boundary. Models had anticipated something like this, but Voyager 1 found the barrier to be stronger and thicker than predicted, almost as if the heliosphere was pressing harder against the interstellar medium than expected. or the interstellar medium was pressing harder back. It is a detail that has implications for understanding the overall shape and stability of the heliosphere, and it has fed directly into debates about whether the heliosphere is more comet-shaped or more spherical than traditional models assumed. Here is the thing most people do not realize about magnetic fields in space. They are not inert. They carry energy. They exert pressure. And in a plasma environment, magnetic fields and plasma are deeply, intimately coupled. They push and pull on each other. They can amplify each other's fluctuations. They can transport energy from one region to another in ways that are genuinely complex to model. When Voyager 1's magnetometer detects a fluctuation in the interstellar magnetic field, that fluctuation is not just a reading on a graph. It is evidence of a physical process, some energy input, some disturbance, some wave or instability propagating through the interstellar medium from a source that may be very far away. Reading those fluctuations is like pressing your ear against the wall of a vast building and trying to reconstruct, from the vibrations you feel, what is happening in rooms you cannot see. The direction of the galactic magnetic field that Voyager 1 is now measuring has an additional significance that goes beyond local physics. The orientation of the local interstellar magnetic field is one of the factors that determines how the heliosphere is shaped, because the external field exerts pressure on the heliosphere's boundaries in a direction-dependent way. If the external field is oriented at a particular angle to the Sun's motion through the galaxy, it will deform the heliosphere asymmetrically, pushing more strongly on one flank than the other, potentially creating a shape quite different from the simple, elongated bubble that early models described. Voyager 1's field measurements, combined with data from other missions, have fed into increasingly sophisticated models of heliospheric shape, and the emerging picture is a heliosphere that is considerably more complex and potentially more compact than anyone had originally imagined. All of this, the missing directional shift at the heliopause, the turbulence in the interstellar field, the magnetic barrier, the implications for heliospheric shape, points toward a truth that Voyager 1 keeps insisting on, measurement after measurement, year after year. The edge of our solar system is not a simple boundary. It is not a clean line drawn across space where one set of rules ends and another begins. It is a zone of interaction, compression, and complexity, where the Sun's influence and the galaxy's influence push against each other in ways that have been going on for billions of years and that we are only now beginning to measure directly. The universe, at the edge of our little domain within it, is pushing back, and the pushback is more intricate, more structured, and in some ways more surprising than we had the imagination to predict. Voyager 1 is our only ear pressed to that wall, listening to what the galaxy is saying just beyond the reach of our Sun. In 2009, a spacecraft that most people have never heard of made a discovery that stunned the astrophysics community and has not been fully explained to this day. The spacecraft was called IBEX, the Interstellar Boundary Explorer, a small, relatively inexpensive satellite placed in a high Earth orbit with one specific and ambitious purpose: to map the entire boundary of the heliosphere from the inside, using a technique that no mission had ever attempted before. Rather than travelling to the boundary the way Voyager had, IBEX would stay near Earth and detect particles arriving from the boundary, energetic neutral atoms, or ENAs, that are created at the heliopause when charged solar wind particles exchange an electron with incoming neutral interstellar atoms and become electrically neutral, freeing them to travel in straight lines back toward the inner solar system. By building up a map of where these particles were coming from, IBEX would effectively be creating an image of the heliosphere's outer edge from a distance. What that image showed, when it first came together, was something no one had predicted. Across the entire sky map that IBEX assembled in its first months of operation, one feature dominated everything else: a bright, narrow band of energetic neutral atom emission, far more intense than the surrounding regions, wrapped around a significant portion of the sky in a great arc, like a ribbon or a belt curving across the boundary of the heliosphere. It did not correspond to any feature in the known models of the heliospheric boundary. It was not aligned with the Sun's direction of motion through the galaxy in the way that the leading and trailing edges of the heliosphere are. It did not match the distribution of cosmic ray intensities or magnetic field directions in any straightforward way. It was simply there, bright, structured, unmistakable, in a location and with an intensity that the models had not predicted and could not immediately explain. Scientists called it simply the ribbon. And a decade and a half later, the ribbon is still not fully understood. The first and most natural question was whether the ribbon was an artifact, a product of some instrumental quirk or observational bias, rather than a real feature of the heliospheric boundary. That possibility was carefully examined and ruled out. The ribbon appeared consistently across different energy ranges of energetic neutral atoms, across different times of year, across instrument calibrations and independent cross-checks. It was real. The second question was what physical process could produce it. A ribbon of enhanced ENA emission concentrated in a specific band across the sky means that the source of those particles, the region of the heliospheric boundary where solar wind particles are being neutralized and sent back inward, is somehow more intense or more efficient along that particular arc than in other directions. Something about the geometry of the boundary or the local conditions along that arc is fundamentally different from everywhere else. The challenge has been figuring out exactly what that something is. Several competing hypotheses emerged in the years following the discovery. One of the leading proposals involves the orientation of the interstellar magnetic field. According to this idea, the ribbon traces the locations on the heliopause where the local interstellar magnetic field is perpendicular to the line of sight from ibex, a geometric condition that would concentrate the energetic neutral atom emission into a narrow band. The physics behind this involves the way that neutralized solar wind protons, after they cross the heliopause and briefly travel through the interstellar medium, can be reionized by the interstellar radiation field and then recaptured by the local interstellar magnetic field. If the field is perpendicular to the direction back to the Sun, these reionized particles get trapped and cycled back inward, producing the enhanced emission signature that ibex sees. It is an elegant hypothesis, but it requires very specific conditions about the interstellar magnetic field geometry that are difficult to verify independently, and subsequent data has complicated the picture in ways the original version of the hypothesis did not fully anticipate. This is where Voyager 1 enters the ribbon story in a particularly interesting way. Voyager 1 is travelling through the region of the heliospheric boundary that ibex was mapping from a distance. Its trajectory carries it through, or at least near, some of the structures that might be producing the ribbon's enhanced emission. The magnetometer data and the plasma wave data from Voyager 1 in the years around and after its heliopause crossing have been used to try to constrain the properties of the local interstellar magnetic field and the structure of the boundary region in ways that can test the ribbon hypotheses. The results have been suggestive but not conclusive. Voyager 1's field measurements are consistent with some aspects of the ribbon's proposed explanation, but do not cleanly confirm or refute any single model. The two datasets, ibex's global map from Earth orbit and Voyager 1's in situ measurements from inside the boundary, are proving to be complementary but not yet fully reconcilable into a single coherent picture. Here is the thing most people do not realize about the ribbon discovery. It is not just a puzzle about one unusual feature of the heliosphere. It is a window into something deeper about the relationship between our solar system and the galaxy around it. The heliosphere does not exist in isolation. It is embedded in the local interstellar medium, and the properties of that medium, its density, its temperature, its magnetic field orientation, its flow direction relative to the Sun, all shape the heliosphere from the outside in ways that are still being mapped. The ribbon tells us that the interstellar environment surrounding our solar system is not uniform and isotropic. It has structure. It has preferred directions. It has a geometry imposed on it by the large-scale magnetic field of the galaxy, and that geometry leaves visible marks on the boundary of our heliospheric bubble. We are not floating in featureless space. We are embedded in a structured medium that pushes on us from all sides in ways that are only now becoming visible. What makes the ribbon particularly haunting to sit with in the quiet of tonight is this. It exists at the very edge of our solar system's reach, in a region that only 2 spacecraft have ever entered, and it was discovered not by those spacecraft directly, but by an observatory sitting close to home, listening for particles that had made a round trip, out to the boundary and back, carrying information about a structure that none of our models had imagined. The universe revealed it not when we went looking in the right place with the right instruments, but almost by accident, as a surprising brightness in a map that was supposed to confirm what we already knew. That is how a lot of the deepest discoveries in science actually happen, not as confirmations, as surprises, as ribbons appearing where no ribbon was supposed to be, demanding an explanation that, more than 15 years later, we are still constructing. Voyager 1 moves through the region where that ribbon originates, and every reading it sends back is another data point in a mystery that has humbled every model we have thrown at it. There is a detail about the Voyager mission that sometimes gets lost in the excitement surrounding Voyager 1's record-breaking distance and its historic crossing into interstellar space. There is a second spacecraft. Voyager 2 launched first, on August the 20th, 1977, 16 days before its twin, and it is also still alive, still transmitting, still doing science, from a position in interstellar space that no other human-made object except its sibling has ever reached. Voyager 2 crossed the heliopause in November of 2018, about 6 years after Voyager 1, at a distance of roughly 119 astronomical units from the Sun, and what it found when it crossed over was both similar enough to confirm the broad picture and different enough to complicate it in ways that have kept scientists busy ever since. 2 probes, 2 crossings, 2 sets of data, and between them, a portrait of the heliospheric boundary that is more complex, more asymmetric, and more surprising than anyone had anticipated when the mission was conceived. The first thing to understand is that Voyager 1 and Voyager 2 did not exit the heliosphere through the same region of the sky. Voyager 1's trajectory, bent sharply upward by its close flyby of Titan during the Saturn encounter, sent it out through the northern hemisphere of the heliosphere, above the plane of the solar system in the direction of the constellation Ophiuchus. Voyager 2, which continued on to Uranus and Neptune before heading outward, exited through the southern hemisphere in the direction of the constellation Pavo. These 2 exit points are separated by a significant angular distance, and they sample the heliospheric boundary in regions that may be subject to different external pressures, different interstellar magnetic field orientations, and different plasma environments. Comparing the 2 crossings is therefore not like repeating the same experiment twice. It is like taking 2 samples from different sides of an object you have never been able to examine directly, and using the differences between the samples to infer the object's 3-dimensional structure. The crossing itself, in Voyager 2's case, was in some ways sharper and more dramatic than what Voyager 1 had experienced. The plasma instrument on Voyager 2, which had unfortunately stopped functioning on Voyager 1 back in 1980 due to a stuck actuator, leaving a significant gap in Voyager 1's instrument suite, was still fully operational. This meant that for the first time, scientists had direct in-situ plasma measurements at the heliopause crossing. What the instrument recorded was extraordinary. The solar wind plasma dropped to essentially undetectable levels almost instantaneously, over a period of just 1 day, as Voyager 2 crossed the heliopause. At the same time, the density of the plasma spiked sharply upward as the spacecraft entered the interstellar medium. The transition was far more abrupt than models had predicted, suggesting that the heliopause in the southern hemisphere was a thinner, sharper boundary than the somewhat more gradual transition that Voyager 1's data had implied in the north. 1 boundary. 2 very different crossing signatures. There was also a temperature anomaly that genuinely shocked the scientists analysing the data. Just inside the heliopause, in the innermost layer of the heliosheath, where the slowed solar wind piles up against the boundary, the plasma instrument on Voyager 2 detected temperatures far higher than any model had predicted. The solar wind plasma in the heliosheath was expected to be cold, having expanded and cooled as it travelled outward from the Sun. Instead, the measurements showed temperatures roughly 10 times higher than the model's forecast. Something was heating the plasma in the heliosheath to levels that had not been anticipated. The source of that excess heat was not immediately obvious. Several mechanisms have been proposed: wave heating, charge exchange processes, turbulent dissipation, but none has yet been confirmed as the dominant explanation, and the temperature discrepancy remains one of the more striking puzzles that Voyager 2's crossing produced. Here's the thing most people do not realise about what it means to have 2 probes at 2 different points on the heliopause simultaneously. The heliosphere is not a static object. It breathes, in a sense, expanding and contracting slightly as the Sun's activity cycle waxes and wanes over its roughly 11-year cycle of magnetic activity. Solar maximum, when sunspot activity peaks and the solar wind is stronger and more variable, pushes the heliopause slightly farther out. Solar minimum pulls it slightly inward. The heliosphere also responds to the external pressure of the interstellar medium, which itself varies as the solar system moves through slightly different density regions of the local interstellar cloud. When Voyager 2 crossed the heliopause in 2018, The solar cycle was in a different phase than when Voyager 1 crossed in 2012. The two crossings are separated not just in space, but in time, and the heliosphere they sampled was not identical in the two cases. Disentangling the spatial differences from the temporal differences is one of the central challenges of interpreting the comparative dataset. Despite these complications, certain differences between the two crossings appear to be genuinely spatial, the result of sampling the heliopause at two different locations around its circumference, rather than artifacts of timing or instrument differences. The boundary layer at Voyager 2's crossing point was measurably thinner than at Voyager 1's. The temperature of the plasma just outside the heliopause in the local interstellar medium was slightly different at the two locations. The strength of the magnetic field just outside the boundary showed subtle differences between north and south. Each of these variations is a data point in the growing picture of a heliosphere that is not a symmetric, uniformly shaped bubble, but rather a complex asymmetric structure shaped by the combined influence of the Sun's varying output, the directionality of the interstellar magnetic field, and the detailed flow properties of the local interstellar medium pressing in from outside. What strikes me most about the two-probe picture is what it implies about how much we still do not know, and how fortunate we are to have even this much. Imagine trying to understand the shape and structure of a vast, invisible bubble surrounding an entire star system using only two data points sampled from two specific locations on its surface, separated by 6 years in time and tens of billions of miles in space. That is precisely the situation we are in. Voyager 1 and Voyager 2 are the only direct measurements we have ever made of the heliospheric boundary from the outside. No other probe has crossed it. No other instrument has touched the interstellar medium from the inside. The entire edifice of our current understanding of the heliospheric boundary, its thickness, its temperature profile, its magnetic field behavior, its asymmetry, rests on two spacecraft built in the 1970s that were never designed for this phase of the mission, and that are running out of power with each passing year. And yet what those two spacecraft have revealed, in their differences as much as their similarities, has transformed our understanding of the boundary between our solar system and the galaxy in ways that will take decades to fully absorb. Voyager 2 gave us the plasma instrument reading we never had from Voyager 1. It gave us a southern hemisphere data point to set against the northern crossing. It gave us the temperature anomaly and the thinner boundary and the subtle field differences, each a clue in a puzzle whose full picture we cannot yet see. Two voices from the edge of everything speaking different dialects of the same language, telling us that the universe just beyond our sun's reach is richer, stranger, and more varied than a single crossing point could ever have revealed. Let us pause for a moment from the instruments and the data and the anomalies, and simply be where Voyager 1 is. Close your eyes if you like, or let your gaze soften in the dark of wherever you're lying tonight, and try to imagine the place this spacecraft actually inhabits right now. There is no sun visible as a disk, only a point of light, bright but distant, one star among the many, distinguished from its neighbours only by the faintest quality of its light, if you knew exactly where to look. There are no planets, no asteroids, no comets, no dust rings catching the sunlight. There is in every direction a darkness so complete and so uniform that the human brain, evolved in a world of surfaces and near distances, genuinely struggles to construct an image of it. This is the interstellar medium. This is the space between the stars, and it is almost, but not quite, nothing. The interstellar medium is one of those concepts that sounds empty until you understand what it actually contains, and then it sounds extraordinary. In the region that Voyager 1 is crossing, the local interstellar medium, the particular pocket of the galaxy in which our solar system currently resides, the average density of matter is roughly 1 hydrogen atom per cubic centimetre. 1 atom, in a space the size of a sugar cube. By the standards of a laboratory vacuum, this is impressively empty. By the standards of everyday life on Earth, where the air around you contains roughly 27 million trillion atoms per cubic centimetre, it is a void so extreme as to be almost inconceivable. And yet it is not nothing. Those sparse atoms are there. That faint plasma is there. The magnetic field threads through it. Cosmic rays stream through it. And the temperature of this near emptiness, measured by the energy of its particles, is somewhere around 6,000 degrees Celsius, far hotter than you might expect for something so sparse, heated by the diffuse radiation field of the galaxy and the energetic particles streaming through it. The cold that Voyager 1 physically experiences, in the sense of the thermal environment its hardware must endure, is a different matter from the plasma temperature of the medium it travels through. The spacecraft itself radiates heat into the surrounding void and receives essentially no compensating warmth from external sources at this distance from the Sun. Its components are kept functional by the residual heat of the RTG power sources, carefully managed by the engineering team on Earth. But the background temperature of empty space, the temperature you would measure if you held a thermometer in the interstellar void, shielded from any local particle flux, is approximately minus 270 degrees Celsius, just barely above absolute zero. The coldest cold there is, the baseline temperature of the universe itself, the faint residual warmth of the Big Bang stretched thin across 13.8 billion years of cosmic expansion. That is the thermal environment of the space Voyager 1 crosses, cold enough to stop almost everything. Cold in a way that the word cold does not adequately describe, and the distances are where the mind encounters its true limits. Voyager 1 has been travelling for nearly 50 years at roughly 38,000 miles per hour, and in all that time, across all those billions of miles, it has not come meaningfully closer to another star. The nearest star system to our Sun is Alpha Centauri, a triple star system about 4.2 light-years away. A light-year is roughly 5.9 trillion miles. 4.2 light-years is therefore approximately 25 trillion miles. Voyager 1, at its current speed and trajectory, would take roughly 73,000 years to reach Alpha Centauri. If it were headed in that direction, which it is not, it will make its closest approach to another star system, a dim red dwarf called Ross 248, in approximately 40,000 years, passing within about 1.7 light-years. Not close enough to be called a visit, just a slow drift past a distant neighbour in the dark, separated by distances that make our entire solar system feel like a grain of sand on an endless beach. This is perhaps the most terrifying thing about interstellar space. Not its cold, not its emptiness, not its silence, but its scale. The distance between stars is so vast that the fastest thing we have ever built, travelling continuously for a human lifetime, barely registers as movement against the backdrop of interstellar distances. If the solar system were the size of a house, the nearest star would be on the other side of a continent. If you shrunk the Milky Way galaxy to the size of North America, our entire solar system would be smaller than a single grain of sand somewhere in the middle of it. Voyager 1, our farthest ambassador, has travelled from one side of that grain of sand to the other. It is now hovering just outside the grain's edge, in the vast plain between sand grains, surrounded by emptiness in all directions, and the nearest other grain is thousands of miles away on this scale. The interstellar medium is not a corridor between destinations. It is the destination itself for anything travelling at speeds we can currently achieve, an endless, ancient, cold expanse that will outlast every civilization that has ever wondered about it. There is something in the quality of this silence that deserves to be named. Voyager 1 does not receive radio signals from other civilizations as it travels through the interstellar medium. No transmission from anywhere in the galaxy has ever been detected arriving at Earth from an identifiable artificial source. The interstellar medium through which Voyager 1 moves is, as far as we can tell, traversed by nothing but natural phenomena. Cosmic rays, magnetic fields, plasma waves, the slow drift of interstellar dust. The silence of the space between stars is not merely acoustic. Sound cannot travel through a medium this thin. It is electromagnetic, informational. The channels through which intelligence, if it existed nearby, would announce itself, are quiet. The galaxy, in the neighbourhood through which Voyager 1 currently drifts, is not speaking in any language we have learned to recognise. And yet there is a strange comfort in the quality of this emptiness, if you let yourself settle into it. The interstellar medium is ancient. The atoms drifting through it have been there for billions of years, produced in the cores of stars that died long before our sun was born, scattered by explosions whose light faded from the sky before Earth existed. The magnetic field threading through it carries the accumulated history of the galaxy's evolution, shaped by events operating on timescales and length scales that encompass the entire lifespan of solar systems. Voyager 1 is moving through a medium that is, in a very real sense, made of the universe's memory. Every atom it passes is a relic. Every field line it crosses is a record. The silence of the interstellar medium is not the silence of emptiness. It is the silence of something very old, very large, and very patient. Something that was here long before we arrived, and will be here long after our sun has burned itself out and grown cold. In that silence, Voyager 1 travels on, and so, tonight, do we. Bolted to the side of each Voyager spacecraft there is a disk. It is 12 inches in diameter, made of copper plated with gold, and sealed in an aluminum cover etched with instructions for how to play it. It is a phonograph record, a technology that was already beginning to feel slightly old-fashioned in 1977 when it was placed aboard, and that most people alive today have never used. On this record are sounds and images selected to represent life and culture on Earth. Music from Bach and Beethoven and Chuck Berry and a Navajo night chant, an Azerbaijani folk song and a Pygmy girl's initiation song. Greetings in 55 human languages and one greeting from humpback whales. The sounds of rain, wind, surf, fire, birds, and a human heartbeat. 115 images encoded as audio signals, including photographs of the Earth from space, a nursing mother, a man eating, children running, a supermarket, and the mathematical definition of our position in the galaxy using pulsar timing signals as a coordinate system. It is called the Golden Record. And the fact that it exists and what it implies becomes more complicated and more haunting the longer you think about it from where Voyager 1 is now. The Golden Record was the brainchild of Carl Sagan, who chaired the committee that designed it, and who approached the task with a combination of scientific rigour and genuine romantic ambition. The stated purpose was straightforward. If Voyager 1 or 2 were ever intercepted by an intelligent civilization somewhere in the galaxy, the record would give that civilization a means of understanding who sent it and something of what we are. It was conceived as a message in a bottle, a greeting cast into an incomprehensibly vast ocean with a full understanding that the odds of it ever being found were extraordinarily small. Sagan himself described it as a cosmic gesture, as much as a practical communication strategy. A way of saying, with the one artifact we were sending beyond the solar system, that we know we are not the whole of what exists, and that we are curious about what else might be out there, and that we chose to introduce ourselves rather than to pass silently into the dark. But here is the question the Golden Record forces you to sit with, in the quiet of tonight. It was sent without any evidence that there was anyone to receive it. The decision to include it was made at a time when the search for extraterrestrial intelligence was young and optimistic, when the sheer number of stars in the galaxy seemed to make it virtually inevitable that other civilizations existed somewhere among them, when the silence of the cosmos had not yet accumulated the weight it carries now. In the decades since Voyager launched, that silence has deepened. The search for extraterrestrial intelligence has grown more sophisticated, more systematic, and more comprehensive, and it has found nothing. No radio signals from identifiable artificial sources, no laser pulses, no gravitational wave signatures of megastructures, no anomalous infrared emissions from star systems harnessing stellar energy at civilizational scale. The galaxy, as best we can tell from every instrument we have pointed at it, is not obviously full of communicating civilizations, and Voyager 1 is now out there in that silence, carrying its golden greeting into a darkness that has not yet answered. This is the Fermi paradox, and it presses hardest precisely when you think about Voyager 1's journey. The Italian-American physicist Enrico Fermi posed the essential question in 1950. If intelligent life is common in the galaxy, where is everybody? The universe is 13.8 billion years old. Our sun is only 4.6 billion years old. There have been billions of years during which other civilizations, if they exist, could have arisen, developed technology, and spread across the galaxy. Even travelling at a small fraction of the speed of light, a civilization with a few million years of technological development could have colonized every star system in the Milky Way many times over, and yet the sky is quiet. No signals, no visitors, no evidence. The interstellar medium through which Voyager 1 now travels shows no sign of having been engineered or altered by any intelligence other than the human hands that built the probe moving through it. The silence is total. And the silence, after everything we have learned about how vast and old and star-filled the galaxy is genuinely difficult to explain. The anomalies that Voyager 1 is detecting in the interstellar medium, the plasma density higher than predicted, the cosmic ray distributions that do not quite fit the models, the magnetic field transitions that surprised everyone have no connection, scientifically, to the question of whether other civilizations exist. They are physical anomalies in a natural environment, and the explanations being pursued for them are entirely grounded in astrophysics and plasma physics. But there is an emotional resonance between these two things, the unexplained readings and the unanswered question, that is hard to ignore when you let yourself sit with both of them at once. We sent a probe into a region we did not fully understand. It is finding things we did not predict, and it is doing this in complete silence, in a galaxy that has given us no indication, after decades of careful listening, that any other mind is out there registering the same puzzles and asking the same questions. The golden record will outlast almost everything humanity has ever made. The copper beneath the gold plating will survive for billions of years in the cold of interstellar space, protected from the chemical weathering that destroys materials on planetary surfaces. The record itself, if it is never intercepted, will drift through the galaxy long after the sun has exhausted its hydrogen fuel and expanded into a red giant, long after Earth has been consumed or rendered uninhabitable, long after every library and monument and digital archive we have ever created has been erased by the slow violence of geological and stellar time. In some sense, it is the most durable artifact our civilization has produced. A copper disc carrying the sound of a heartbeat, and the music of Bach and a greeting in 55 languages, moving silently through a darkness that has so far given no sign of containing anyone to hear it. And yet I find something in the golden record that is not entirely melancholy. There is a defiant optimism in its existence that feels important to acknowledge. The people who designed it did not know that the search for extraterrestrial intelligence would come up empty for the next half-century. They did not know that the Fermi paradox would deepen rather than resolve. They knew only that the universe was vast and old and full of stars, and that it seemed worth introducing ourselves to whatever else might be in it. That instinct, to reach out, to communicate, to assume that curiosity and wonder are not unique to us, is one of the more admirable things our species has ever expressed. Voyager 1 carries that instinct with it into the interstellar medium, through the anomalies and the mysteries and the unexplained readings, past the place where our sun's influence ends and the galaxy's silence begins. The question it asks by its very existence, are we alone in all of this? Is one that tonight, as you drift towards sleep beneath a sky full of stars, you share with everyone who has ever looked up and wondered. There is a number that the engineers at NASA's Jet Propulsion Laboratory track with a particular kind of careful attention. It is not a distance measurement or a cosmic ray count or a plasma density reading. It is a power figure, the number of watts that Voyager 1's radioisotope thermoelectric generators are currently producing. When Voyager launched in 1977, that number was approximately 470 watts. Today, nearly 50 years later, it has fallen to somewhere around 240 watts. It drops by roughly 4 watts every year, as the plutonium-238 in the RTGs undergoes its slow, inevitable radioactive decay, and the thermoelectric converters that turn its heat into electricity degrade from decades of operation in the radiation environment of deep space. 240 watts sounds like enough. It is roughly the power of 2 bright incandescent light bulbs. But keeping a spacecraft alive and communicating across 24 billion miles of empty space on that budget requires a level of engineering discipline and strategic sacrifice that is, in its quiet way, extraordinary. The story of Voyager 1's power management over the past 2 decades is the story of a series of goodbyes. Each instrument, each heater, each subsystem that is no longer strictly essential has been evaluated, weighed against the power it consumes, and, when the math demands it, switched off permanently. The plasma subsystem heater was turned off years ago, which is one reason the plasma instrument that would have been so valuable for the heliopause crossing was already dead. The ultraviolet spectrometer was shut down in 2008. The planetary radio astronomy instrument followed. Each shutdown was a deliberate, carefully considered decision made by engineers and scientists who understood exactly what scientific capability they were giving up, and who made the calculation that preserving the remaining instruments for as long as possible was worth the loss. It is resource management in one of its most poignant forms, a team of human beings on Earth deciding year by year which eyes and ears their farthest ambassador gets to keep. Currently, Voyager 1 has 4 science instruments still operating. the magnetometer measuring the direction and strength of the magnetic field threading through the interstellar medium, the plasma wave science instrument, detecting the oscillations of plasma that have given us those crucial density measurements, the cosmic ray subsystem, counting the high-energy particles streaming through interstellar space from distant galactic sources, and the low-energy charged particle instrument, measuring the flux and energy distribution of lower-energy particles in the spacecraft's environment. Together, these four instruments represent humanity's only direct sensor suite in interstellar space. They are returning irreplaceable data from a place that no other probe has reached, and they are running on the power of a dim light bulb, maintained by engineers who know that the margin for error is essentially zero and is shrinking with every passing year. The projected timeline for Voyager 1's eventual silence has shifted over the years, as engineers have found creative ways to squeeze additional operational life from the aging hardware. For much of the past decade, the working estimate was that the spacecraft would lose the ability to power even a single science instrument somewhere around 2025 to 2030. Recent power management decisions, including the shutdown of a backup system that was consuming power without providing essential function, a fix implemented as part of the response to the 2022 computer fault, have potentially extended the operational window slightly. But the physics of radioactive decay does not negotiate. The power curve is dropping. At some point in the not very distant future, there will simply not be enough electricity to run the heaters that keep the remaining instruments from freezing solid in the interstellar cold, or to power the transmitter that sends the data home, or to maintain the computer systems that manage the spacecraft's orientation and operations. And on that day, Voyager 1 will go silent. What happens after that silence is something worth sitting with. The spacecraft will not stop. It has no engine running, nothing to slow it down, no friction in the near-perfect vacuum of interstellar space to bleed away its velocity. Voyager 1 will continue travelling at roughly 38,000 miles per hour essentially forever, or at least for timescales so vast they dissolve into abstraction. In 40,000 years, it will make its closest approach to the red dwarf Ross 248, passing within about 1.7 light-years. In about 300,000 years, it will pass within a few light-years of another star. Over millions and billions of years, it will drift through the Milky Way, subject to the slow gravitational stirring of the galactic disk, its trajectory gradually randomizing until it becomes, in effect, just another piece of interstellar flotsam, a manufactured artifact moving silently through the galaxy, with no one listening to it and no way for it to announce what it is. The golden record on its side will still be there, the copper will still be intact. But the voice that made it meaningful will have been gone for an almost unimaginable span of time. Here is the thing most people do not realize about what we stand to lose when Voyager 1 goes quiet. It is not merely the loss of one spacecraft among many. There is no replacement coming. No mission is currently funded or approved to send another probe into interstellar space on a timescale that would fill the gap before Voyager falls silent. Proposed missions, including an interstellar probe concept that NASA has studied in various forms for years, would require funding commitments, development timelines, and launch windows that place any potential successor decades away at the very minimum. If Voyager 1 falls silent in 2026 or 2028, there will be a gap of potentially decades during which humanity has no direct measurement capability in the interstellar medium. All the anomalies we have been exploring tonight, the plasma density, the cosmic ray distributions, the magnetic field behavior, just will go unmonitored. The universe's answers to our questions will stop arriving, and we will be left with the questions alone, unable to gather new data until a new mission is conceived, built, launched, and travelled for years or decades to reach the boundary. There is a particular kind of grief in this that does not have a precise name. It is not the grief of losing a person, though the community of scientists and engineers who have spent their careers with Voyager describe the prospect of its silence with an unmistakable personal weight. It is something closer to the grief of losing a sense, of knowing that a window onto a part of the universe that no other instrument can see is about to close, and that when it closes, the view from that window will be gone for a very long time. Every piece of data that Voyager 1 sends back between now and its final transmission is therefore not just scientifically valuable in the abstract. It is irreplaceable in a literal sense. It is information about a place we cannot otherwise reach, gathered by instruments that are not otherwise available, returned across a distance that no other mission is currently crossing. Each transmission is a gift. Each anomalous reading is a clue that may sit unresolved for decades. And the clock, running on the slow decay of a few kilograms of plutonium bolted to the side of a spacecraft in interstellar space, is counting down with a patience and an indifference that no human urgency can alter. We have travelled a long way tonight, from the launch pads of Cape Canaveral in 1977 to the interstellar medium beyond the heliopause, from the pale blue dot photograph to the plasma density readings that do not match the models, from the magnetic field that failed to shift at the crossing to the ribbon that appeared where nothing was predicted to appear, from the computer fault that nearly silenced our farthest ambassador to the slow countdown of its diminishing power supply. We have covered the breadth of Voyager 1's journey and the depth of what it has found. And now, before we arrive at the close of tonight, it is worth pausing to gather all of those anomalies together, to lay them side by side and ask, with honesty and with the appropriate humility that real scientific uncertainty demands, what they might collectively be trying to tell us. The first anomaly, the magnetic field direction did not rotate clearly at the heliopause crossing. The solar magnetic field and the interstellar magnetic field were expected to meet at a discernible angle, producing a measurable shift in the direction that Voyager 1's magnetometer would detect as it crossed over. The shift was smoother and less dramatic than predicted. Several explanations have been proposed: a favourable geometric alignment, a more gradual transition zone, a need to revise the models of heliospheric magnetic structure, but none has achieved full consensus. What this anomaly suggests, at minimum, is that the interface between the Sun's magnetic domain and the galaxy's magnetic domain is more complex and more continuous than the simple boundary layer models assumed. The two magnetic environments do not simply end and begin. They intermingle, overlap, and transition in ways that reflect the dynamic, turbulent nature of plasma physics operating at enormous scales. The second anomaly, the plasma density in the interstellar medium just beyond the heliopause is higher than predicted, and it appears to increase as Voyager 1 moves deeper into the local interstellar medium, rather than levelling off into the uniform background density the models forecast. 3 independent plasma oscillation events over more than a decade of travel have all returned density values at or above the high end of model predictions. The most likely class of explanation involves the heliosphere itself, having compressed and enriched the interstellar plasma in its immediate neighbourhood over billions of years, a kind of local enhancement created by the very presence of our solar system pushing against the surrounding medium. If this is correct, it means the interstellar medium sampled just beyond our heliopause is not a clean, pristine sample of the wider galaxy. It is a locally modified environment, shaped by the long-term interaction between the Sun's output and the surrounding interstellar gas. The heliosphere has left a fingerprint on the space just beyond its own boundary, and we are only now learning to read it. The third anomaly, the cosmic ray flux outside the heliopause, does not match the models in its detailed energy spectrum and directional distribution. Anomalous cosmic rays, particles that should have been left behind inside the heliosphere, persist in detectable quantities beyond the heliopause. The intensity and angular distribution of galactic cosmic rays show subtle but reproducible departures from the standard diffusion models used to predict cosmic ray propagation through the interstellar medium. What this suggests is that the processes governing how energetic particles move through the interstellar medium are more complex than the relatively simple diffusion models that have served as the standard framework. The interstellar magnetic field is not a smooth, uniform guide for cosmic ray particles. It is turbulent, structured on multiple scales, and capable of creating preferred pathways and trapping regions that simple models do not capture. Voyager 1's cosmic ray data is, in effect, a direct probe of the small-scale structure of the interstellar magnetic field, information that cannot be obtained any other way. The fourth anomaly, the ribbon discovered by IBEX, that arc of enhanced energetic neutral atom emission concentrated along a band of the sky that no model predicted, remains without a fully accepted explanation more than 15 years after its discovery. The leading hypothesis involving the geometry of the interstellar magnetic field is plausible and partially supported by Voyager data, but it has not produced a quantitative model that fits all the observational details. The ribbon is a feature of the heliospheric boundary that our best theories did not anticipate, and its persistence as an unsolved problem is a reminder that even the boundary of our own solar system, the most local example of a stellar wind bubble we can study, contains structure that current physics has not fully accounted for. Every stellar system in the galaxy presumably has a heliosphere equivalent. The ribbon tells us we do not yet fully understand what those boundaries look like, or how they interact with the surrounding interstellar medium. Here is the thing most people do not realize about what these 4 anomalies mean, taken together. They are not 4 separate mysteries requiring 4 separate explanations that happen to arise in the same place. They may be 4 different instruments looking at 4 different aspects of a single, underlying truth about the nature of the heliospheric boundary and the local interstellar environment that we have not yet fully grasped. The magnetic field behavior, the plasma density enhancement, the cosmic ray distributions, and the ribbon could all be manifestations of a more complete picture of how stellar wind bubbles interact with the interstellar medium, a picture that our models have approximated but not yet captured with full accuracy. The anomalies may not be contradictions of physics, they may be invitations to better physics, clues pointing toward a more complete theory of how stars and the interstellar medium coexist and interact across the billions of years of galactic history. What is striking about this moment in the history of space science is that we are in a genuinely rare epistemic situation. We have one probe in interstellar space, and it is aging. We have a set of anomalies in its data that are real and reproducible. We have a community of scientists actively working to explain them, proposing models, testing them against the data, refining them in response to the results. And we are doing all of this against a clock that is running down, knowing that the data stream will end within a few years, and that we cannot send a follow-up instrument quickly enough to fill the gap. This creates an urgency in the scientific community around Voyager data that is unusual in a field where patience is normally a foundational virtue. Every month of continued operation is precious. Every plasma oscillation event, every cosmic ray count, every magnetometer reading is a data point that may prove essential to eventually resolving these mysteries, or that may instead become part of an unfinished dataset handed to future generations to complete. I want you to carry something with you from tonight's journey through these anomalies. The fact that Voyager 1's data does not perfectly match our models is not a failure. It is not a reason for anxiety or disappointment. It is exactly what good science looks like in practice. The universe is not obligated to conform to the theories we build to describe it. It is always more complex, more textured, more surprising than our best current approximation. Every anomaly is an opportunity, a place where reality is trying to tell us something we have not yet fully heard. Voyager 1. This 50-year-old machine running on the power of a light bulb in the cold dark between the stars is the universe's messenger to us. And the message it is carrying, in those anomalous readings and unexpected densities and unexplained ribbons, is the most honest thing science ever has to say. We thought we understood. We were close. But there is more. There is always more. There is an old human practice, ancient and persistent across cultures, of placing a message inside a bottle and releasing it into the sea. The person who does this knows, with almost complete certainty, that the bottle will never reach a specific destination. They know that the ocean is vast and the odds are small, and that most bottles sent this way end up on a beach somewhere unexpected, or sink, or drift for decades without ever being found. And yet people do it anyway. They write the message, they seal the bottle, they release it into the water and watch it go. Because there is something in the gesture itself, in the act of sending a message outward into an uncertain expanse with the hope, but not the expectation of it being received, that feels true to something deep in human nature. The hope is not the point. The reaching is the point. Voyager 1 is the grandest version of that bottle that our species has ever made. And tonight, as we arrive at the end of our journey together, I want to sit with what that means. Voyager 1 was built by human hands in the 1970s. It was designed by human minds working with the best knowledge and the best tools available to them at the time. It was launched by human ambition, the genuine, unironic ambition of a civilization that looked at the outer solar system and said, we want to know what is out there, and then built something capable of going and finding out. For 4 years it did exactly what it was designed to do, visiting Jupiter and Saturn and sending back images that rewrote entire chapters of planetary science. And then it kept going. It went past the edge of what it was designed for, past the edge of the solar system itself, past the boundary of the sun's dominion, into the interstellar medium where no human artifact had ever travelled, still speaking, still listening, still doing science with instruments built by people, who could not have known where their machine would eventually end up. There is something in that persistence, in the simple, mechanical fact of its continued operation, that feels like it means something beyond the purely technical. The anomalies we have explored tonight, the plasma density that does not match the models, the magnetic field that did not shift as predicted, the cosmic rays arriving at unexpected angles and intensities, the ribbon that appeared where nothing was forecast, are real. They are in the data. They have been verified and cross-checked and published and debated by the scientific community. They are not evidence of anything supernatural or inexplicable in principle. They are evidence of a universe that is more complex than our current models, a boundary region that has more structure than we anticipated, an interstellar medium that has been shaped by forces and timescales that dwarf our ability to directly observe or simulate. They are, in the language of science, productive anomalies, the kind of discrepancies that do not overturn a field but deepen it, that do not invalidate what we knew but extend it into territory where the old maps run out and the new ones have not yet been drawn. But here is what I want you to carry beyond the science, into the quiet of whatever night surrounds you now. Voyager. One is out there in the interstellar medium, moving at 38,000 miles per hour through a darkness so complete and so ancient that our minds cannot hold it directly. It is alone in a way that nothing else we have ever made is alone. The nearest star is tens of thousands of years of travel away. The signal connecting it to the human beings who built it takes more than 22 hours to make the crossing. And yet that connection exists. That thread of radio waves thinner than imagination is real. Engineers in Pasadena check it every day. Scientists in universities around the world study the data it carries. A community of human beings is paying attention, carefully, devotedly, urgently, to what a machine the size of a small car is measuring in the space between the stars. The connection between Voyager 1 and the people who listen to it is, in its way, one of the most extraordinary relationships our species has ever maintained. We are the universe noticing itself. That phrase has been said before, in various forms, by various scientists and philosophers who are trying to put into words the strange vertiginous fact of consciousness existing in a cosmos that operated for nearly 14 billion years without anything in it being aware of its own existence. Hydrogen collapsed into stars. Stars forged heavier elements in their cores. Those elements scattered into space when the stars died. New stars formed from the scattered debris, with planets orbiting them, and on at least one of those planets, in conditions that remain somewhat mysterious even now, chemistry became biology, became something that could think and wonder and build and ask questions about where it came from and what surrounds it. We are made of the universe. We are the universe having an experience of itself. And Voyager 1, this bottle cast into the ocean of stars, is the furthest extension of that self-awareness that we have ever managed to achieve. A piece of the universe, assembled by the universe, sent back out into the universe to look and listen and report. What Voyager is detecting now that no one can fully explain is not a threat and not a crisis. It is an invitation. It is the universe doing what it has always done to the minds that pay attention to it, offering more complexity than the current framework can hold, nudging the models toward greater accuracy, pulling the boundary of the known outward by another increment. The plasma readings and the magnetic field data and the cosmic ray distributions are the universe's way of saying the map is incomplete. And here is where the edge of the known gives way to the unknown, and here is where the next generation of understanding will begin. Voyager 1, running out of power in the interstellar dark, sending back its faint 22-hour signal across a distance that breaks ordinary intuition, is doing the most human thing imaginable. It is reaching. It is asking. It is refusing to accept that the boundary of what is known is the boundary of what is knowable. Thank you for staying with me tonight, all the way to the edge of everything we have ever sent into the dark. It has been a long journey, and a quiet one, and I hope it has given you something to rest inside. Not answers, because the universe is not finished offering those but wonder. The good kind, the kind that does not frighten, but expands. If tonight's journey meant something to you, if the story of Voyager 1 and the mysteries it is uncovering in the interstellar medium felt worth your time, please take a moment to like or subscribe. It is a small gesture, but it is how this channel reaches more curious minds who might want to make this journey too. The next time you find yourself outside on a clear night, look up. The stars you see are separated from each other by distances so vast that Voyager 1, after 50 years of travel, has barely scratched the surface of crossing even one of them. And somewhere out there, moving through the dark between those points of light, a bottle is still travelling, still carrying its message, still speaking in a voice that takes 22 hours to reach the ears of the people who are listening. Sleep well tonight, and keep looking up at the stars. Good night.